if you want to dig a hole faster, your instinct probably tells you to just grab a bigger shovel.
Right, obvious.
You just want to take these massive, heavy scoops out of the dirt to get the job done. I mean, it makes intuitive sense. Bigger bites equal faster results.
It definitely does make sense. But today we're looking at a stack of technical briefings and engineering data from ISCAR, and it proves exactly the opposite is true.
At least when it comes to modern manufacturing, right?
Exactly. If you take that bigger shovel logic and try to apply it to cutting solid metal, you are going to run into some highly destructive problems.
And by destructive, we mean?
Very destructive. I mean, you will snap your cutting tools, you'll warp your materials, and you honestly risk stalling out incredibly expensive multi-million-dollar machinery.
Oh, wow. So just pure brute force doesn't work?
Not at all. In the world of machining, brute force is basically the exact opposite of efficiency.
Which brings us to the mission for today's deep dive. Whether you're an engineer or, maybe someone managing a production floor, or you're just insanely curious about how the physical objects around you are made.
Yeah, everything from jet engines to smartphone cases.
Right. Efficiency is the name of the game. So we're exploring a highly specialized, somewhat counterintuitive strategy called high-feed milling.
Yeah, high-feed milling, or HFM.
Yeah.
And the entire premise relies on this paradox.
The idea that taking much shallower cuts into a piece of metal can actually result in, higher productivity.
Exactly. Drastically better tool life and just a faster overall process. It's a brilliant shift in perspective, really.
Because for decades, traditional milling really did rely on that bigger shovel approach, didn't it?
It did. If you wanted to remove material, you made these deep, heavy axial cuts. You literally plunged the cutting tool deep into the block of metal and just tried to plow right through it.
Ouch. Sounds violent.
It was. But high-feed milling completely flips that script. The strategy is to take exceptionally shallow depths of cut, but advance the tool across the metal at incredibly high feed rates.
Okay, let's unpack this, because if I am just, skimming the surface of the metal, it feels like I'm doing less work.
Right, it looks that way. But to really understand how we get more output from taking smaller bites, we have to look at the underlying physics.
Okay, hit me with the physics.
Well, according to the engineering data, the real secret here lies in the geometry, specifically the entering angle of the tool itself.
The angle it hits the metal.
Exactly. Conventional tools might hit the metal at a steep, nearly 90-degree angle. But high-feed milling tools use a very low entering angle, specifically somewhere between 10 to 20 degrees.
Okay, so 10 to 20 degrees. Why that specific number?
That 10 to 20 degree window is really the mechanical sweet spot. To understand why, you have to sort of visualize where the kinetic energy goes.
Right, because you have a spinning piece of carbide violently colliding with a solid block of steel.
Exactly. And in conventional milling, when you take a deep cut with a steep angle, a massive percentage of that cutting force is directed radially.
Radially meaning sideways, right? Perpendicular to the tool.
Yeah, pushing sideways, it's pushing laterally against the cutting tool itself, and it's also pushing sideways against the workpiece.
And I imagine that lateral force is pretty bad for precision.
It's the absolute enemy of precision. It causes the tool to bend slightly as it spins, a phenomenon we call deflection. And that deflection creates a tremendous amount of vibration.
Let me see if I have this right physically. It sounds like the difference between skipping a stone across a pond versus dropping a massive boulder into the water.
Oh, that's a really good analogy.
Right, because if you take a heavy, deep plunge with conventional milling dropping the boulder, you displace a lot of material, sure.
But you create this massive turbulent resistance.
Exactly. The water violently splashes back in all directions. But with high-feed milling, utilizing that shallow 10 to 20 degree angle, it's like skipping the stone.
Yeah, it's fast, it's light.
And the energy is directed smoothly and horizontally over the surface rather than, fighting the entire depth of the water at once.
That is a perfect way to visualize it. And what's fascinating here is what happens to that redirected energy.
Because it has to go somewhere.
Right. Because of that low 10 to 20 degree entering angle, the cutting forces aren't pushing sideways against the tool anymore. Instead, the geometry translates that horizontal motion into an axial force.
Axial force.
Meaning the energy is pushed straight up the shaft of the tool, directly into the machine's spindle.
And the spindle is the part of the machine that's actually spinning the tool, right?
Right. And the spindle is basically the most robust, massive, and rigid part of the entire machine.
So it can take the hit.
Exactly. Its bearings are specifically designed to handle vertical axial loads. So by sending the force straight up into the spindle, you drastically improve the stability of the entire operation.
Oh, wow. So you practically eliminate that sideways deflection.
You do, and you neutralize the vibration and the chatter that normally ruins the cut.
Okay, well, the physics check out on paper. I understand how shifting the angle sends the force into the strongest part of the machine.
Yeah.
But in reality, if I am taking thousands of shallow impacts on my newt, conventional tool edges are just going to fatigue and shatter.
Oh, absolutely they would.
So how do you engineer a physical piece of metal to survive that kind of rapid-fire mechanical stress? I mean, without it just shaking itself apart.
Well, that is the big hurdle ISCAR had to overcome to actually industrialize this physics concept. They had to design tool bodies and inserts that truly thrive in this environment.
The briefing details some specific setups, right?
Yeah, they call them systems, like Logic 4 feed or Hilly Do feed. And the architecture of these tools is wildly different from traditional cutters.
Okay, let's look at the Logic 4 feed system, because honestly, this raised a huge red flag for me.
Really? How so?
Well, the data mentions it uses a multi-insert system with 4 cutting edges per insert. When I read that, my immediate thought was, like, a disposable multi-blade razor? Are they just acknowledging that these high speeds destroy tools, so they just give you 4 edges to burn through quickly?
It's actually the exact opposite of that. It's not about burning through edges at all. It's about graceful wear versus catastrophic failure.
Graceful wear. Okay, explain that.
In a traditional setup, when you're taking a deep, heavy cut, the wear is concentrated in one single spot, and it's often violent.
Right, because of all that lateral force.
Exactly. You get sudden microchipping, or the edge just completely shears off because it's bearing the brunt of that massive sideways pressure.
But with these high-feed inserts.
Because that low-angle force is distributed so evenly and pushed up into the spindle, the wear on the tool is fundamentally different.
It's more spread out.
It's spread out and highly predictable. The wear on these incredibly robust cutter bodies develops gradually over time.
So no nasty surprises.
Right. You don't have operators constantly slamming the emergency stop button because a tool unexpectedly shattered inside an expensive aerospace part.
That sounds incredibly stressful.
It is. And having 4 cutting edges on a single insert just means that when an edge finally does reach the end of its natural, predictable lifespan, the operator simply unscrews it, rotates or indexes the insert 90 degrees to a fresh edge, and starts again.
Ah, so it just maximizes the amount of metal you can remove per dollar spent on carbide.
Exactly. It's highly efficient.
There's another hardware element mentioned here, damped tool holders. I imagine those are crucial for scenarios where you can't just have a short, stubby tool right next to the spindle.
Precisely. Like if you have to reach deep into a cavity.
Right.
In machining, anytime you have a long tool overhang, meaning the cutting edge is physically far away from the spindle, housing vibration becomes an absolute nightmare.
Because it's just dangling out there.
Yeah, a long spinning piece of metal naturally acts like a tuning fork. If you apply a sideways radial force to a tuning fork, it sings, it vibrates wildly.
But because high-feed milling forces are directed straight up the axis of the tool,
it doesn't strike the side of the tuning fork. Combine that axial force with a damped tool holder, which actually has internal mechanisms to absorb resonance, and you get perfectly stable performance.
even when reaching deep into a complex part. That is so cool.
It really is.
Wait, hang on, though. I'm thinking about the actual speeds involved here.
Okay.
If you're feeding the tool into the metal that much faster, isn't the friction going to just multiply exponentially?
It's a valid concern.
I mean, even with a shallow cut, if you are hitting the metal at 3 or 4 times the normal speed, shouldn't the tool just melt into a puddle?
That is the logical assumption, yeah. And it brings us to one of the most elegant mechanical phenomena in machining, the chip thinning effect.
Okay, what is chip thinning? Because honestly, that sounds like something that happens to my snacks in the pantry, not a piece of industrial steel.
I get that. So think about the actual metal shaving that is carved off by the tool. That's the chip.
Okay, got it.
When metal is sheared away, about 80% of the heat generated by the friction goes directly into that chip.
Wait, 80%?
Yes. The chip is actually the vehicle that carries the heat away from the tool and the workpiece. And because of that shallow 10 to 20 degree entering angle we talked about earlier, the physical geometry of the cut stretches and thins the metal chip out as it's formed.
So instead of carving off a thick, chunky curl of metal, it's shaving off a very wide, microscopically thin ribbon.
Yes, exactly. And because it's so thin, it forms much faster and evacuates away from the cutting zone instantly.
Taking all that intense heat with it.
Taking the heat with it. This chip-thinning geometry actually requires you to run the machine faster.
Wait, really? You have to go fast?
You do. If you feed the tool too slowly, it will just rub against the metal instead of slicing it cleanly. And that rubbing is what would cause catastrophic heat buildup. The speed is actually what makes the cooling mechanism work.
That is wild. But the tool itself still has to get incredibly hot, right? I mean, the chip takes away 80% of the heat, sure. But that remaining 20% is still thousands of degrees of thermal energy?
It is.
Standard steel isn't going to survive that.
It absolutely weren't, and that's why these tools aren't made of standard steel at all. ISCAR utilizes advanced tungsten carbide substrates.
Right, the briefing highlights some specific metallurgical grades, like their IC830 or IC808.
Yeah, and they engineer these at a literal molecular level.
So the documentation talks about these carbides having a tough core combined with PVD and CVD coatings. And honestly, trying to visualize a tough core with a coating, my first instinct was to compare it to like a baked cake with a hard frosting.
A cake with frosting.
Yeah, but a cake doesn't deflect thousands of degrees of heat.
No, a cake would definitely incinerate. A much better way to look at it is to think of the heat shield tiles on a space shuttle re-entering the atmosphere.
Oh, okay. That makes much more sense. Walk me through that.
So the substrate, the carbide core of the tool is like the structural body of the space shuttle. It's dense, it's shock absorbing, and it's designed to withstand immense physical impact without snapping in half.
But the substrate alone can't survive the thermal shock of reentry. Or, cutting metal.
Exactly. So they apply PVD, which stands for physical vapor deposition, and CVD, chemical vapor deposition.
And what are those processes actually doing to the tool?
They are essentially vaporizing highly wear-resistant metals, like titanium aluminum nitride, inside a vacuum chamber. Then they deposit them ion by ion directly onto the carbide core.
Wow.
Yeah, it creates this incredibly thin, armored phase barrier on the surface of the tool. Just like the silica tiles on the space shuttle, this coating is designed to absorb, deflect, and resist extreme thermal energy so that the structural core underneath doesn't melt or deform.
And the briefing mentions that this thermal stability prevents something called thermal cracking. What is that?
Well, think about what happens to the tool edge during a high-speed milling operation. It spins into the metal, experiencing violent friction and extreme heat, and then a millisecond later, it spins out into the open air where it cools down slightly.
Oh, I see. Heating up, cooling down, thousands of times a minute.
Exactly. It's expanding and contracting constantly.
And that constant micro-expansion and contraction will literally pull the surface of a standard tool apart.
It does. It creates these tiny fissures called thermal cracks. But the PVD and CVD vapor-deposited coatings act as a thermal insulator, smoothing out those extreme temperature spikes and preventing the carbide from fracturing in the first place.
If you've ever wondered why aerospace components or high-end medical implants are so incredibly expensive, it's largely because of this exact thermal puzzle.
It really is. Machining advanced alloys usually means you are constantly throwing away ruined, melted tools and running your machines at a snail's pace.
So solving this thermal dynamic is literally how you make jet engines cheaper to produce.
Exactly right. When you combine the predictable wear of the shallow cuts with this molecular heat shield technology, it completely changes the economics of the manufacturing floor.
Because manufacturers get drastically higher spindle utilization.
Yes, meaning the machine is actually doing its job, cutting metal, instead of sitting idle while an operator changes out a broken tool.
And they get faster cycle times without needing to invest in a brand new $2 million machining center. They are literally just upgrading the physics of the process itself.
That's the beauty of it.
It's like downloading a software update that optimizes how your car's engine handles combustion, suddenly making the car twice as fast. You didn't buy a new car, you just engineered a smarter way to use the horsepower.
I love that. It's a strategy upgrade driven entirely by material science.
Okay, so we have the force vectors figured out, and we have these indestructible space shuttle tools.
Yeah.
What are we actually cutting with them? The source lists some materials that sound like an absolute nightmare for a typical machinist.
Oh, they are the toughest materials on the planet. High-feed milling excels in hardened steels, stainless steels, and heavy tool and mold steels.
But where it really flexes its muscles is in the aerospace and energy sectors, dealing with superalloys, right?
Yes. We're talking about aerospace-grade titanium and heat-resistant superalloys like Inconel.
Okay, Inconel is infamous. It's used in the exhaust sections of jet engines because it maintains its strength at extreme temperatures.
Exactly.
But that same property makes it notorious for eating cutting tools alive. It undergoes something called work hardening, doesn't it?
It does. Machining Inconel is a bit like trying to run across a pool filled with a non-Newtonian fluid. You know, like cornstarch and water.
Oh, yeah. Like the science experiments kids do. If you step lightly and quickly, you can move across it.
Right. But if you stomp down hard, the fluid instantly locks up and becomes as hard as concrete.
So that's what the metal does.
Basically, when a conventional milling tool takes a deep, slow bite into Inconel, the friction generates so much heat that the metal actually hardens right in front of the cutting edge.
Wow. So the harder you hit it, the harder it fights back.
Exactly. And the tool just gets obliterated against this newly hardened wall of superalloy.
But with high-feed milling.
By utilizing those incredibly fast, light strokes, the tool gets in, shears off that microscopically thin chip to carry the heat away, and gets out.
Before the Inconel has time to soak up the heat and work harden.
Yes. It entirely bypasses the material's primary defense mechanism.
That is just brilliant. And the source also notes that this method is incredible for complex geometries. It mentions pocket roughing, where you have to hollow out a deep cavity inside a solid block, and something called helical interpolation.
Helical interpolation.
Yeah, I'm assuming that's not a complicated dance move.
No, not quite. Helical interpolation is when the machine moves the spinning cutting tool in a continuous downward spiral, kind of like a corkscrew tube bore a large hole or cavity into solid metal.
Okay, makes sense. But when you try to corkscrew a conventional tool deep into a block of titanium, the lateral forces we talked about earlier will often cause the tool to bind up and snap inside the hole, right?
Usually, yes. It's highly risky.
But because our high-feed tool is pushing all that force straight up the spindle, it stays rigid.
Right. The shallow cuts mean there's very little tool engagement with the sidewalls of the hole.
So it doesn't get stuck.
Exactly. The machine can effortlessly execute these complex, multi-axis spiraling tool paths with virtually no risk of the cutter binding or snapping.
Now, there is a crucial nuance here, though, that we definitely need to clarify for the listener.
Very true.
As revolutionary as this geometry and chemistry combination sounds, high-feed milling is not some magic wand that completely replaces every other tool on the shop floor.
No, it isn't. The briefing is very specific that HFM excels in roughing and semi-roughing operations.
And that distinction is vital. It really raises an important point about manufacturing strategy.
It does. Knowing which physical principle to apply to which phase of the job is what separates a good engineering team from a great one.
Right.
High-feed milling is designed to remove a massive volume of material as quickly and safely as possible. That's the roughing phase.
You're just trying to take a raw block of titanium and get it as close to its final shape as you can in record time.
Exactly. But because you are using that fast, shallow, skipping stone technique we talked about, the surface left behind is going to be slightly scalloped.
It isn't going to leave you with a mirror-smooth finish.
Right. For those final finishing operations that demand ultra-fine surface tolerances, or, in certain cases where you absolutely need a perfectly straight, deep, 90-degree wall.
Conventional milling is still required for that.
It is. High-feed milling does the heavy lifting, getting you 90% of the way there safely and rapidly, so your conventional finishing tools can come in, take a tiny whisper of a cut, and provide the final 10% polish.
So it's all about playing to the mechanical strengths of the tool.
Precisely.
Let's take a step back and sort of recap this journey, because it's a perfect example of how challenging a fundamental assumption can alter an entire industry.
It really is.
We started with the basic intuitive assumption that a bigger shovel means faster digging, that deeper cuts remove metal faster.
But by shifting the entering angle to that 10 to 20 degree sweet spot, we redirect the destructive radial forces safely up into the machine's spindle.
Removing the deflection, neutralizing the vibration, and completely stopping the tuning fork effect.
Yes. Then you combine that ingenious geometry with advanced material science. The carbide substrates protected by vapor-deposited heat shields that act like space shuttle tiles.
And finally, you deploy it using industrialized hardware systems designed to manage predictable wear gracefully, like the Logic 4 feed.
Right. The result is that manufacturers can chew through the most punishing superalloys on Earth-like work-hardening Inconel faster and more reliably than conventional physics would suggest is even possible.
And that reliability is the ultimate goal, isn't it?
It is. Predictable wear means less machine downtime, fewer destroyed aerospace parts, and a far more efficient operation from start to finish.
Which really hits at why all of this matters to you, whether you're standing on a production floor programming a machine, or you're just fascinated by the hidden logistics that create the modern world.
Exactly.
In a highly competitive environment, gaining a tangible edge isn't always about brute forcing the problem or pushing your machines to the breaking point. It's about engineering a smarter mechanism.
It's about working smarter, not harder.
Yeah, it's about looking at the physics, understanding the vectors of force, and realizing that sometimes taking a smaller, faster scoop is the actual secret to moving a mountain.
We've seen today how meticulously engineering the geometry and the molecular chemistry of a cutting tool can completely redefine its efficiency.
It changes what we think is physically possible in machining.
It does, but it leaves you with a fascinating question for the future, I think.
Oh, what's that?
Well, we've optimized this 10 to 20 degree angle based on human engineering and decades of trial and error.
Right.
But as artificial intelligence begins to model complex physics and material sciences natively, what happens when AI starts designing these microgeometries and alloy coatings completely from scratch?
Oh, wow.
What happens when an algorithm designs a tool based purely on quantum physics without any human biases about what a cutting tool should look like? Will the cutting tools of the next decade even be recognizable to the human eye?
That is a wild thought to leave on. A tool that looks completely alien, but copes with perfect mathematical efficiency.
It's coming.
That's a perfect place to wrap up today's deep dive. Keep questioning the obvious, keep exploring, and we'll catch you on the next one.